Yeah, so this is partly a repetition of a talk I gave in February, but A, I've gone a lot further, but B, I have a new angle, which is talking about computer algebra facilities and the whole idea of integrating computer algebra with theorem provers. So this is an old idea. The idea that if you got two good things, you might not want to have them at the same time. So computer algebra is good, theorem proving is good. Can we combine them? I said this is a very old stream of work. People notice there are many ways in which computer algebra systems are unsound. Sometimes they simply have bugs. Sometimes they're a little too optimistic about what you can simplify out. So yes, of course, x is not equal to 1 there, so we can divide the x minus 1 factor out of both sides and this sort of thing. And they don't have any logical capabilities. And meanwhile, back in the early 90s, when people were trying to do this, you could still struggle to prove that like x plus y equals y plus x. So you can see why people wanted to combine these two technologies. They didn't get as far as they would like. And one real problem was a convincing application, like what are you really doing this for? And if you look in certainly most mathematical textbooks, you do not see the kind of complicated integral that needs a computer algebra system. I don't mean textbooks teaching you how to do complicated integrals. I mean textbooks doing mathematics. Normally the integrals are simple, whatever they do, it's normally not the monstrous things people throw at computer algebra systems. So anyway, lots of papers were published and people forgot about it. But over time, various things went into Isabelle Hall. Well, I'm just going to go through these before I move on to the application, which was that big paper that caused such a fuss last year. So, and by the way, if any of you are really familiar with computer algebra, it is a big, big field, and there are lots of really sophisticated, powerful algorithms that work at scale. I am not pretending we do anything on that level. Nevertheless, we have some computer algebra capabilities that are automatic or almost automatic and are pretty useful for, let's say, the monster proof I will tell you about in the second half of the talk. So these are basic things, right? You know, I will tell you in more detail what some of these are. The root finding and counting winding numbers things, I'm not actually going to go into anymore. So the simplest thing you would want to do is take a derivative. So like you see that formula up there, e to the minus t cos 2 pi t. Taking derivatives is not complicated. You can write a computer program that does it with a very little effort. What I'm showing you there, you see that line. What I'm trying to do is show you how it works. So there is the formula, x to the minus x times cos, etc. Then I want to say there exists an f prime, which is the derivative of it. And now my problem is if I just say there exists a derivative, it will find the derivative and then say proved, and that isn't actually very interesting because you want to know what the derivative is. So I just said, well, let's suppose we have an arbitrary property P, and we want to show P of this derivative. Then if I do this, I will be left with showing P of the derivative, and finally I will be able to see what the derivative it actually computed. And now that line there, it's a kind of very level thing in Isabelle that says, take the following rules and just keep bashing it with them repeatedly. And I stopped it there, so you see the cursor, that red block is right after that line, because I have, if you like, stopped the computation here so that you see kind of what it's doing in the middle here. So in the course of breaking up this thing, it has come up with a bunch of identities to be proved. Now these, you probably don't know how Isabelle works, but you have these unknown variables that can be unified. It's like Prolog. It's a lot like Prolog, and this is a lot like a Prolog program. So if one continues this, this will be solved by saying, right, that thing will equal 1, this thing will equal -1, and on and on and on. Now, of course, nobody wants to do this. And this is just, I wanted to show you what's happening inside. What you would actually do is this. So there I said, repeatedly try one of those things or use a powerful tactic that will prove it. And that will then do the job in one step. And here is our derivative that has been calculated. What's interesting is it's been simplified as well. If you ever tried writing a computer program to take derivatives, you get a lot of awful messes. And it's nice that here it somehow came out simplified. We'll see an awful mess in a moment. Sorry, what I have there, I showed you in the animation, the extra tactic being called to get rid of those silly subgoals we saw on the previous slide. Now you'll say, what about integration? Well, the bad news is Isabelle can't integrate. The good news is Maple can. So go to Maple and say, integrate that, please. And it says, yeah, this. And the nice thing, actually, if you copy out that thing in Maple and paste it into Isabelle, the underlying syntax is that different. So with a little bit of editing, it's in Isabelle. And then all you have to do is take the derivative and check that you've got what you started with. And so here we are. I am trying to check that this thing, which was the integral, has the derivative, the thing I started with. Now, on this time, we don't finish the proof because we get this unsimplified mess I told you about. And if you look closely at that, you'll see, again, if you've ever written a program to take derivatives, this 0 times x and 1 times 4 have to get all over the place. That's just because computers are stupid. But in this case, you add a simplification step and it's proved. So we now have the inverse relationship that we know that the one thing is the integral of the other, and we can even then go on to evaluate definite integral if we want to. Now, for a more powerful thing, I need to praise the work of Manuel Iberl. I don't know everything in this package, so I will just demonstrate a couple of the things for you. So I don't even quite know what a multi-series expansion is. But it's basically for all kinds of limit claims. The limits are found and the claim is proved logically. So here's an example. These are all his examples. So the limit of this monstrosity is 23 over 24. So the way you do that, you just put in the formula. In this case, I think I know the limit already. I think it can calculate the limit as well. I'm not sure. If not, you use Maple to find the limit and then you put it in. Now, this is a real thing, and it is not a joke. Using a computer algebra system to give you answers, which then you check by proof, is a standard approach. So just calling his tactic, which is called real asym, and bingo, that's proved. Or Landau symbols. So how do we formalize this one? Looks a little ugly. So if C is greater than 1, this function that raises a number n, well, sorry, the function that raises n to the k is little o of the powers of C. And again, you just call it and it's done. And it doesn't take long either. A cooler example is this one here. So what have we got? The red line is 1 over 1 minus x. The dark blue line is ln x. And this, by the way, is 1/2. It's not 0. Or the x-axis there is 1/2. So 1 minus x is indeed less than or equal to ln x, but you can't take the limit to 0 itself because, of course, they're undefined. And this is the kind of thing that gets really nasty. But if you just put in at right 0 there, you're telling it to stick on the positive part, and again, it's done automatically. Another thing, now this sounds really dumb, like why not just get a calculator? But you can't put a calculator and stick that in your proof, can you? And by the way, just yesterday, I was at a talk where somebody needed 2 to the 55 minus 19, which he had typed into Hall Light, like he had calculated it using Maple and shoved it in. And he could have written 2 to the 255 minus 19 in Isabelle, and it would, again, be solved in no time. So this one here is called by this approximation practice, which is using interval arithmetic, which is a sound method of doing exact arithmetic. Here is another example. The number is some kind of measure of the precision. It's not decimal and it's kind of arbitrary, but it's a useful thing. And finally, a more sophisticated one. This is a really tricky thing. You see, interval arithmetic alone is not going to help you if things are exact. So x squared less than or equal to x. They are exactly equal at 0 and 1. And generally, interval arithmetic is no good if things exactly coincide. So I don't exactly know what is going on here, but it's doing something clever and it's able to prove this as well. So we've got all this cool stuff. So is it good for anything? Well, now I need to mention Ramsey's theorem. Okay, so, and I assume you all know what Ramsey's theorem is. However, I suppose in case someone doesn't, I just have to remind you. So you've maybe all seen this example where if you have 6 people at a party, there are either a group of 3 people who all like each other or a group of 3 people, all of who can't stand each other. And there's actually a very elegant little proof of this, which I'm not going to do. And what I've done here is a typical party, and the slightly darker blue is the triangle, which I was trying to avoid. And this time I was very careful. I didn't get a triangle until I drew the very last line. And you're welcome to try and change colors of things and see if you can do any better, but in fact you can't. So we say then that the Ramsey number of 3 and 3 equals 6. That means if you have at least 6 people at your party, there will definitely be what is called a clique. So this blue triangle is a, what do they call it? Monochromatic 3 clique, meaning it's all one color and it's a clique and there are 3 things in it. Now, I just want to mention, because Ramsey's theorem is always trivialized to graphs and parties. So I just want to mention it is a bit bigger. In the case of r equals 1, you're dealing, so Ramsey's theorem in its general form is not dealing with edges. An edge is a 2-element set, right? It's in its general form, you can have sets of any finite size. Now, if you have 1-element sets, it's just the pigeonhole principle and nobody cares. If you have sets bigger than 2, you have this, well, a hypergraph form, they call it, and then the Ramsey number calculation resembles Ackermann's function and goes into the stratosphere very quickly. You also have, even the graph case can be made infinite so that your clique sizes can be arbitrary ordinals or cardinals, and again, it's a big subject out there. Anyways, enough of that. What about going back to the simple party case? As I mentioned, the Ramsey number of 3 and 3 is 6. 4 and 4 is 18. Now, 5 and 5, we're already looking at open questions. In fact, this lower bound of 46 was just published, I think, a few months ago, and it hasn't been confirmed yet. Now, this can be like the most tedious work in the world to say, right, this particular fully finite problem, which could be solved if we had a really powerful computer, you could just calculate it, but numbers are too big. Now, in general, we have upper and lower bounds on Ramsey's theorem as follows. And by the way, the two things do not have to be equal. They often are, but they don't have to be. So it's called on the diagonal if the two parameters are equal. So you see this lower bound of square root to the k, it must be at least that. The upper bound given by this binomial coefficient, which is less than 4 to the k. And that has been the state of knowledge for a very long time. People have, including in our own department, so Andrew Thomason worked on this, people have tried to improve these bounds, and there are various minor improvements until I guess it must have been about March 2023 when somebody reduced the exponent by a tiny epsilon, and this is a sensational result. Now, I don't really know Ramsey theory enough to know why apparently people were like spilling their coffee and things when they saw this come through. I mean, how did they even know it was right? I mean, there are several proofs of the Riemann hypothesis on ARC, if you know, just take a look. So, but someone believed this. I guess they knew the author or something like that. So we now know that 4 can be replaced by 4 minus a very small epsilon. And I want to go through not so much the proof itself, which is not my subject at all, and I barely understand it, but the formalization of it. And before I can get there, I should mention how the original 4 to the k bound can be proved. So there is a very simple algorithm you can imagine for finding, remember our problem, you have your party and all the edges colored red or blue, which corresponds to either people like each other or they hate each other. And you are trying to find either a red clique, that is to say, a part of the graph where all the edges between them are red, or else they're all blue. So a way we can do this is you dump all the vertices of the original graph in this set X, and then you just iterate in a very dumb way. So you pick some vertex X at random, and you ask, does it have more red neighbors or more blue neighbors in the set X? If it has more red neighbors, you move it into A, and you throw away from X everything that is not red. In other words, all the blue neighbors you throw away. Now, the point of that and what this red blob means there is that everything in A, all the edges between them are red. So there's a red clique in A, there's a blue clique in B, and moreover, all the edges between big X and A, they are all red. By construction, equally, all the edges between elements of here and B are all blue, because at every step, when we move something into A, say we threw away the ones that didn't satisfy that property. And the other thing, I hope I should have stressed again, we are starting with a complete graph that we're coloring with 2 colors. So clearly you're not losing more than half the elements each time. So you're throwing away all the ones with blue edges and you're keeping the ones with red edges, and you've taken the one with the larger number of edges to begin with. Okay, the opposite case, if the X you chose has more blue neighbors than X, then you put it in B instead, and you throw away everything that does not, that is not a blue neighbor of this thing. So everything in B has only blue neighbors with X, everything in A has only red neighbors with X. You keep doing this. Now, what's going to happen? Eventually, you'll run out of stuff in X, but these cliques are getting bigger and bigger. But if you are able, so if the size of X at the beginning is at least 2 to the k plus L, then you'll be able to run this k plus L times, after which one of them, either A or B, will have, A might have K elements, B might have L elements, either in which case you have found a monochromatic clique of the right size and you're done. And the point is, this little algorithm is completely dumb because you're just picking X at random. So could you do better with a more complicated algorithm? So the new paper that these guys published, there's the title and abstract. I think one of these guys is here. Not, I mean, here. Well, it would have been nice if he were, but here in this department. And I should mention, I guess you all know Bhavik Mehta. I think he's moved on. He formalized this. In fact, I wouldn't have even dreamt of trying this if he hadn't gone and done it first, because I wouldn't have had any confidence that it was possible to do. However, I didn't merely copy what he was doing. Just want to say that. So what is in this paper? They have their much more complicated algorithm, and then they have section after section in which they are basically proving one thing after another about the operation of the algorithm. In fact, if you're a computer scientist, you say, well, it's kind of verification of a completely crazy program. So they set up their program, and by the way, the program is completely infeasible to run, even in principle, because the numbers it deals with are so large. But they are basically proving in a very, what looks recognizably to me like program verification, statements about the size of the various things it's operating on, which ultimately they get the result. And what's interesting from the computer algebra point of view is they're using limits all the time. They're doing numerical calculations regularly, and sometimes these calculations are to like 6 or 8 digits. They have to be really precise. And there's lots of Landau symbols too, which I have to say freaked me out a bit, but we must do things. So I just want to sketch out what it looks like. So we are interested in these, remember, the blue clique, I guess, would be of size L if you find one, the red one of size K, and N, which is, of course, the size of the graph. And these are the basic parameters of the algorithm. Of course, the graph is assumed to have its edges colored, and there are no cliques in it. So that's our basic assumption. We have not just X, A, and B, but also a Y. Quite figured out what Y was doing, but I hope you don't expect I understood the paper just because I verified it. And we have all red edges between those and all blue edges between those, and the diagram, which is somewhat stolen from the paper, is showing you this. So there's X, there's Y, the A, set A with its red clique, B with its blue clique, X, which is now a very carefully chosen element, and the variance. And where you have these thick red lines, it means all the edges between the two sets are all that color. Right, so just to give you a taste of the kind of math being done here, this is standard stuff if you've done anything like they call it these large theories of large graphs and so on. You'll have seen things like edge density. That's a standard definition. He's very interested in the density of the red edges between these sets at X and Y. And yes, what you see, the original algorithm I showed you, the naive one, was symmetric in red and blue. So this one is asymmetric. So he's trying to build a red peak. He's treating the blue stuff in a very different way. And somehow, after all this work, they get this epsilon, which is, I can't remember, 2 to the -7th or something like that. But it's greater than 0. So I'm not going to go through these in detail, just to say he has these they have these 4 different steps their automaton can do, which have these names: degree regularization, big blue, red, and density boost. Maybe I should mention a thing. Remember, the previous algorithm moves 1 vertex at a time, but here in a blue step, you are moving a fuck ton of vertices. because that's a Ramsey number there. And these are big numbers. So this is unimaginable number. I mean, as I told you, this algorithm is infeasible. And one reason it's infeasible is we don't even have a way of calculating that Ramsey number, let alone storing it. If there exists this huge number of vertices with this lots of blue neighbors, then you dump the whole lot into B. Otherwise, you do things that are kind of like the previous algorithm. So in a red step here is like in the previous algorithm, except Y is doing something. As I said, I never really figured out what Y was doing. And there, this again is like in the previous algorithm. Okay, anyway, that is a very rough idea of their automaton. Now, what do these proofs look like? First of all, what do they look like in Isabelle? I guess most of you have never seen Isabelle code. It looks kind of like computer code. This is one part of the algorithm. So what is the next state given X, Y, A, and B, which are the sets? There are the parameters L and K, which control it. And there's this mysterious thing called mu, which is another parameter which influences the operation of this thing. And I've written it rather abstractly like this many bluish predicate, which is abbreviating the exact condition they have under which you do this big blue step. So those are three of the four steps it can do. And then the fifth one, the fourth kind of step is done on every even clock cycle, whereas the other three, one of them is chosen on the odd clock cycle. So this is a very, very simple iteration going around. Very simple bit of code. There's way more to define it. I just wanted to show you what it looks like. Now, what do proofs look like? Well, here is the first thing they prove. And for a computer scientist, I look at the first line and say, be an integer, yeah. So is that the floor or the ceiling of L to the 1/4? I have no idea. And then so I would look at Bobek's proof or something, and he used the ceiling, right? I'll use the ceiling. Likewise, L to the 2/3 there. Another weird thing. X contains a red K clique. Well, they've already assumed that X does not contain a red K clique, so I really wondered why that was there. So what I had to do is show the existence of the blue book. And it was pretty horrible. But there is the final theorem. Oh, I should have updated this. This is a shame. It's an old, it looks nicer than that now, I think. That is a very, very old form it took. But then, never mind, I proved it. Yeah, I need to update that. Now, one of the real sting in the tail, which they had said that L and K can be as large as you want. But what I hadn't grasped is that every theorem has an implicit wording for sufficiently large L and K blah. Meaning, at any point where you're stuck or don't know how to prove something, you ask yourself, would this be true if I could make L as big as I wanted? And very often they say, oh yeah, it would. And then you say, okay, I'm going to take that thing, as long as it only depends on mu, and then add it to the list of assumptions that is required. So you see the statement here is actually, this is one way of saying, for all sufficiently large L and for all K, and that thing implies it, K is greater than L, all that stuff. I later found a more elegant way of expressing it. This is closer to the way Bobek did it here. So, and I just want to mention what was involved. So in the first 3 weeks I did this, there was some background stuff to do. Like the Erdős lower bound for Ramsey numbers is kind of outside the scope of the paper. It's basic preliminary stuff. And I'm very grateful to Andrew Thomason for sketching out the proof of this. This uses a probabilistic proof, so it's kind of a cool thing. And then there's another probabilistic proof in the paper, which we'll see in a moment. So here's, again, part of the proof. This is this is less than a page, this proof, so it's relatively easy, right? So you never mind exactly all what this says, but I could just mention the first equality is by definition, but then you have this one here. So I needed to figure out what these edges were doing, which is a bit of a problem. And I think both of these only hold for a sufficiently large K. And I noticed again, peeping at Robert, that he changed the 1 to a 2. Now you might say, how can you get away with that? And the thing is, because you can make K as big as you want, and this annoying little factor of 2 is something that you can somehow get rid of by making K just like twice as big as before, or something of that sort. But it seemed impossible to get rid of the 2 there, and I thought if it was good enough for him, I would do the same. But this is not the proof of the thing I showed you. It's merely a small part of the proof of the thing I showed you. So here is a calculation. So if you can see, there's at the very top, mu multiplied by some cardinalities of sets less than or equal to something or other, which is part of the edge density calculation, which is needed to prove part of the inequality on the previous slide. Then continuing, this is a probabilistic proof. So you have this set, there's a certain set U. You choose a subset of a certain random size. We know what B is. So you need to set up a probability space to do the probability proof. That is all right. This biconvexity was a real killer, I think. What convexity? What is that? So eventually I worked out that the thing that is a convex function is the binomial coefficient in there. You know, if you generalize the binomial to real numbers, which you can do, then it makes sense to talk about convexity. The only problem being the function isn't actually convex where you need it to be. So again, here's where I had to look at Robert to see, well, he made another function which agrees with this one on the integers, which is the only place you need it, and is convex. I do think that is a little gap in the paper. But anyway, this was horrible. And yeah, so, but getting a uniformly chosen random subset is actually, although it looks scary, it is not difficult once you have figured out how you pull out the right pieces from the libraries to do that. This is not a difficult step. And there we are choosing a random subset. So you see we are choosing an array sets. We get the cardinality of that thing. Then we set up like 5 lines down the uniform probability space and so on. And the trick, you know, with these probabilistic proofs, I guess you all do them at some point, is that you have a set, you set up a probability space, you show that the set's probability in the space is greater than 0. Bingo, it's non-empty. Constructivist howl at this point, and you're finished. And if you don't like that, I mean, what the probability calculation is doing is just a very nice way of expressing a counting argument, which you would use instead, which constructivists would like. Right. Now I very briefly hit on what happened in further sections. So the authors are worried about the density of red edges between the sets X and Y. They want to know that it does not decrease too much. They also need to show that these sets are not used up too quickly. And having done that, that's several sections, that's many pages of proofs. Finally, they're able to get some new results. First, they get some new results far away from the diagonal, which I guess no one would spill their coffee over. But then finally, they're able to get the diagonal as well. That is in the case where K equals L. And that's it. And I did actually manage to prove this whole thing, although it Took me longer than Buffett, despite the ability to cheat by peeking at what he did when I got stuck. Anyway, I want to mention some computer algebra aspect to the formalization, since that's what the talk is about. So, as I mentioned, basically every lemma in the first several sections is implicitly for all sufficiently large L. And what this means is, I think these came from the very first thing, the lemma 4.1. You go through your proof, and anytime you say, I really wish L were at least this big, you say, okay, this, fine, you can have it. Or this. So you can accumulate these. How do you know that there is that for all sufficiently large L, these things will hold? Well, what I would do, and I do have a Maple license, thank heavens. First, I would peek at them and say, oh, yeah, that looks like it might be true. And then you call this real asymp, and which does it in most of the time. Now, there is a slight problem, which has turned out to be the case later in the paper. All of these limit claims have to be proved not for a fixed value of mu. So this mu parameter is what governs all this, you see. It's not enough to prove it for a fixed value of mu, but for a range of mu's within the 0-1 interval, a closed interval of mu's. And you need to have the same L for that whole interval. So the way you do that, I was able to check all the inequalities we had were either going up or going down, which meant you could just pick the worst end, show that the limit held, let's say it's going up, be less than something. So you say, right, you check the limit at the worst end using real asymp, and then you use whatever hopefully simple argument that the thing is going to decrease as you go across the interval. So there are a lot of technical details to do to get this to work. Now, in the beginning, I was keeping track of these inside the theorem and just kind of handing them together, as you can see. And finally saying, yeah, you can see that I'm proving this conjunction of things by breaking it up and finally calling real asymps to prove them all. Later, it seemed to me that it was nicer to make all these conditions explicit. So what I've got here for lemma 7.6, I need seemingly the thing for 7.8, the thing for 7.12, for some other theorem, and for some other theorem. I need them, all of them at the same time. So I just add them all together and say that is what I mean by a big enough L for this particular theorem. And you just keep accumulating these things until you get to the end. And of course, it's an absolutely humongous conjunction, but you never have to look at the whole thing. And it's always necessary to prove that they are satisfiable. In other words, that there really is an L such that for all bigger L, the thing holds, because otherwise you've made an assumption that is never going to be realizable. Okay. And yeah, just sorry, highlighting the real asymp call for you. There it are. And this is the trick for dealing with those ranges of intervals that I told you about. Right. So this was, I found this so gruesome. What does 2 to the OK even mean? So I asked one of you guys was very helpful. Probably here, I'm really embarrassed. I acknowledged you, however. So you just have to find an OK function and then raise 2 to it. That's all. So what they want to show here, they want to show that y remains big enough. So y0 is the original value of y, and they want to show that as you run the algorithm, the size of y will continue to be at least 2 times this small number times its other stuff. So we have all these O of k functions, little o of k functions, lying around in the proofs. So for example, this is the thing we had to prove. I formalize the O of k function, which in this case is something awful. It's that big ugly formula there. How do you know it's O of k? Well, you just call real asymp. Very grateful for that. And finally, now the statement of this particular lemma, which is lemma 7.6, you see what we do is we assume we have an L which is big enough, and then we prove the conclusion holds using that fact. And then when we are in the middle of the proof, when we need some part of the various properties that have been assumed, then we split it up and use them. Sorry, I just can't stop showing off the real asymp calls. So here is another thing. See, it's kind of interesting that you've got these numerical calculations. Why does it say greater than 0.667, greater than, I think they could have left off one of those. Anyway, here I have left out part of the argument, but all I am showing you is we got this function which they were talking about. I think this refers to that function. Yes, so C of x, this is this function here. I'm wanting to show that this thing is greater than 2/3. And there we are. I'm showing it at both ends. I need to show it's true over the whole range. I prove this function is concave, which is hidden from you. Then I show simply by evaluation, this approximation method I told you about, that it's greater than 667 at the bottom end. It's also greater than it at the top end. And then by concavity, then it's greater over the entire interval. Again, and I'm sorry if this is tedious. I'm just trying, there you are. The calls, aren't they cool? Showing that you can do these things even involving exact calculations in a proof in a real paper. Now this was a motherfucker. And by the way, now the epsilon in the thing I proved was not 2 to the minus 7, it was 2 to the minus 11. So at some point, trying to show that a certain thing is always less than that, and that will eventually, this is almost at the final hurdle here that you have got to show this thing. Now I'm hiding from you all those definitions, but that is what we had to show was less than 2 to the 2 minus 1, 2 to the minus 11. Over that interval, you see, why is it 0.341? Where did they get all these numbers from? I have no idea. But this is a thing you have to show, and I actually needed help here to call the approximation method with the splitting parameter to try and get it. Because this is really close. So this inequality is true, but it gets really, really close, which is why well, this takes like 15 seconds to run. So
what does y equal 13 mean?
Y is the variable here, and I think it is allowing 13 levels of splitting. So it might be 2 to the 13 split.
Okay.
13, and then you do our interval, you do each of the small cells.
Okay, so yeah.
Because it's more precise than just one big one.
Yeah, I'm not sure if it's 13 or 2 to the 13. Given how long it, as I said, I mean, almost everything here runs very, very, very quickly. So this whole development mostly runs quickly, and then there are 2 calls like this, and they each take 15 seconds. And that really stands out. So anyway, so I did find an application of computer algebra in a proof. So there's really, this is a real proof, right? If people noticed. And it is absolutely full of real computer algebra things, and it's full of arithmetic that very, very fine calculations. I don't know how much mathematics looks like this. So we have these methods. I said approximation is fast. It's mostly fast, but it is not fast in that particular example. We can also do differentiation. And yeah, the proof as a whole was pretty gruesome. There is the main result. So theorem, there exists an epsilon, which is a real number, positive with the property that for all sufficiently large k, the Ramsey number of k and k is less than or equal to 4 minus epsilon 2k. And that is, of course, just the outer form, calling all those other things that I was talking about. So as it says, 11,000 lines of Isabelle. It takes 9 minutes in all to run. Of which half a minute is just those calculations there. And yeah, it took me longer than Pavlik. But then he's a mathematician. So yeah, Mantis, you're here. Yes, you're the one who told me what to do with okay. Yeah, thank you. So Simon is one of the authors who answered some queries. There is actually a couple of significant errors in the paper, which he helped me with, and so on. And by the way, Pavlik is a talk at the Lean together in, probably last January, which he actually understands the proof, which means his talk is a lot clearer. That's all I have.
Yeah, thank you very much. Do we have questions?
Yeah.
So I seem to remember that one of the reasons why Thomas Hales got into proof assistance from his kind of double proof of the Kepler conjecture was in part because there were a lot of kind of computation of like integrals and things like that. So we're like, how this compares to the sort of thing that you're doing now, because now the Kepler stuff was quite a while ago.
Yeah, ironically, I don't actually, the approximation proof method was done around 2008, and it is conceivable that it was used, but I don't think so. Most of the Kepler conjecture thing was done in Hall light.
Yeah.
There would only one part was done in Isabelle, which was some graph theoretic thing.
So you don't know how much kind of computer algebra thing.
I don't know in any detail what that proof looks like. I barely know what this proof looks like.
Thank you.
In the beginning, you were using the force tactic. What does that do exactly?
Okay, so Isabelle has a bunch of closely related automatic tactics. I don't know how many Isabelle users are even here, but there's one called Auto, which is designed to kind of run fairly quickly and give you all the stuff it doesn't know how to prove. And it's these days, it's thought to be bad form to use Auto and then have a bunch of random stuff and then prove them one after another because the proof is a bit messy. So one can still use that to see what the random stuff is, and in an exploratory phase, try and will give you ideas how to maybe prove it better, but first you have to get your horrible proof before you get a nice one. Force is very similar to Auto, but it only terminates if there's nothing left.
Okay.
So it insists on proving everything.
Oh yeah, how many lines of code is it?
2 at the same time. Yeah, do you want to go?
So how many lines of code is it?
11,000.
11,000, okay.
And the De Broglie factor is higher than usual because for other work we've done, it was 4. Now, the De Broglie factor means ratio, done in a fairly clever way. I think the De Broglie was in 6 or maybe even 8. Okay. Horrible stuff. You had a question as well?
Yeah, I just kind of regarding the theorem. So you said it's like 1/2 to the power of 11, but that's still for our large enough k, right?
Yeah.
So we do not know exactly what the epsilon is.
No, the epsilon is 2 to the minus 11.
Yes, but it holds for arbitrary k.
Yeah,
You're asking for all k.
For all sufficiently large k, the epsilon of 2 to the minus 11 works.
But it,
There's a trick, because for all values, so you prove this epsilon is like 2 to some epsilon. For all k greater than some fixed number, and you know what that fixed number is. And you also know that all the Ramsey numbers before that fixed number are strictly less than 4 to the k.
yes.
So you can just pick just like the tiny epsilon, which kind of goes over like between 4 to the k and the values at k equals. Blah, blah, blah.
This tiny epsilon can be smaller than 2 to the minus 1.
Oh,
Yeah, yeah,
you're
that's what
trying, yeah, what you're trying to do is say that there's an epsilon for all k. I don't think they ever said that, but I mean, the argument you gave would work, of course. I mean, I was unfortunately forced to do things like that on occasion. Again, there are little things where they have overlooked some small thing. Making it worse, actually, for a lot of the paper, the thing they call epsilon is k to the minus 1/4, I think. So their epsilon, the thing they call epsilon, actually depends on k, which would make nonsense of the whole thing. But then finally, the epsilon that they arrive at the end is in fact 2 to the minus 11. Now, one thing I would like to claim, I think the actual proof formal document doesn't look too bad. And given that when you look at the actual proof and you see all these numerical things that they've arbitrarily said, well, this will be 2/5, and this is 3.341, and so on, you might wonder, how did they arrive at these, and what happens if you change them? And could we get a better proof, a bigger epsilon? Could we shorten something by somehow tinkering with it a little bit and changing things? And this is a thing where someone who is interested could say, right, I'm just going to change that 3 to a 4 and see where it breaks and think, can I fix this? Now, of course, it's stupid for me to do it because I have no idea how this damn thing holds together. But for people who understand how it's meant to work, they could say, all right, I could do it this, and then I could get, epsilon could be, 2 to the minus 5. Yeah.
Thank you for the talk. I'm wondering, you made it very clear that you didn't understand the proof.
Yeah.
Would you, but would you say that you could do this for any sort of sufficiently well written up proof? Or do you think that there need to be special conditions for you to be able to prove it?
I think I would like to have the author of the paper kind of, if I could call them up whenever I'm stuck and say, like, is that a floor or a ceiling? And yeah, that's a floor, right? But that one's a ceiling. That would be incredibly helpful. This kind of stuff, it's just, for my mind, every time you see a thing like that, it's a little demoralizing. You think, oh, holy shit, again. And it was like, there would be a whole series of really tough problems. And I figured out that I could generally solve one tough problem a day. So then the rate of actually making progress is one tough problem a day, plus you need extra days to do the routine stuff. And yeah, with the help of someone who knew what was going on, it would have been a lot easier.
And do you think that you need to have the proficiency in Isabel on your level, or do you think you could put graduate students on these kind of things, even though they're not understanding
Well,
them?
a lot of graduate students are pretty smart, and I think when I see other people's Isabel, I mean, the quality varies, but often it's very good. Hi, Yaliki.
9 minutes to run, right?
The whole thing, yes.
Very weak, different developers. That have, that can run much faster, or just so you have an idea of what you're running.
This is actually much longer than, you know, the things we did, I forgot the name, what was that, first graph theory thing that Cody? Oh, yeah, so this Chemeretti regularity lemma, and of all those examples, I think none of them took more than a minute or a minute and a half. There's these proofs I'm doing at Amazon, which I can't tell people about now. That they take a long time. The incompleteness theorem proof that takes several minutes, I think.
Are there any hardware limitations?
Well, that's actually on a relatively old, that's on a 2019 x86 machine. So I think there are faster machines I could consider doing it on. But yeah, I think in terms of running the whole thing can take 9 minutes, but actually working, there's not much of a delay when you're most of the steps are pretty instantaneous. And of course, you need that, otherwise you go insane with it. Oh, and I should have said the 9 minutes is the CPU time, thanks to, I mean, it's multi-threaded, so the actual elapsed time is like 2 minutes.
And do you have any questions on that?
Sure.
So like, you used Maple for some things.
Yeah.
Do you think it would be reasonable to hope that these things could be done by Isabel in some distant or not so distant?
Well, a
future?
lot of the things I use Maple for do not need proof. So very often I'm asking, it's like, I can't prove this. Does this hold if K is big enough? And sometimes I see, oh, it's going the wrong way. This is just not true at all. And then I've fucked up somewhere, you know. So I would often just fooling around and doing calculations.
You're saying that basically this was your oracle at hand to just play around, and
Absolutely.
there was not much point in.
I didn't have a mathematician by my side, but at least I had Maple, so I could at least say, right now that's not concave, that's convex actually, or whatever, you know.